All right, so we'll do some last kind of minute review, just to kind of review what I said Friday about the exam. It's open all day today and tomorrow. You can get on at any time and take it. Once you start, you'll have 90 minutes, so an hour and 30 minutes to start. So that means if you want the full hour and 30 minutes, the last you can kind of start it is 10:30, right? Because it closes at midnight or tomorrow night. Sorry. There is a bonus question on there, so it'll be scored out of 104 points, kind of similar to the last one. So until everybody's taken it, I won't be able to update the scores to be out of 100. So once everyone's taken it, I'll kind of re-upload. Kind of, it looks like a separate exam, but it'll be basically the same exam, just scoring it out of 100, which actually will improve. Whatever you see after you take the exam, if you get an 80 out of 104, you actually have an 80 out of 100, so your grade will end up being a little, have a little bit higher percentage there. Any questions just kind of about taking the exam, not necessarily like specific problems, but just anything related to the logistics? Kind of get those questions out of the way if there are any. Yep, so 18 multiple choice and then one big short answer. So kind of similar to last time, you can do your work in Excel, Word, take pictures of it. You're doing it by hand. You can upload all of those for the short answer problem. Show me as much work as possible. In fact, I'll try to show you today why that would be important as we kind of work through a couple problems. But if you show me all your work, it's a lot easier for me to kind of give some partial credit, even if you're not 100% correct on those. Okay? And that's related to the short answer question. I think it's got 5 parts to it, so it's I think it's worth 28 points. Multiple choice are worth 72. So it's about 30% of the grade. Any other questions kind of about logistical stuff? Okay. So there's no questions there. Are there any specific problems on either of the practice exams that people want to work through? Otherwise, I'll probably kind of pick and choose to work through some stuff that I think will be helpful. Are there any specific questions on any problems? Where's my chat? Okay, I guess you're left to my mercy. One thing I would start out saying is just kind of having a good idea of what the equations in this formula sheet are. So just kind of to do a quick review. Like if I was doing this maybe as the open the PDF or the Word, then kind of either you could use comments in PDF or you could like insert some text, right? To kind of help you get all this sorted. Well, if we go all the way back, oops, and this is, you could add comments. I'd probably use Word and just add text boxes. But I don't want this here actually. There we go. So if I wanted to put, what is it? Some text here or kind of write something here, I would identify these 4 equations. Notice they're kind of grouped together. These are my uniform distribution equations. Okay? We'll go through a problem here in a second that uses these. This is just kind of a reminder that the standard deviation is just the square root of the variance. Here's if we're just dealing with a normally distributed variable. Here's how I can convert that value for x into a z-score. This reminds me how to find the standard deviation and the variance of my sample means, right? Just dividing by the sample size. Similarly, how I find the variance and standard deviation for my distribution of sample proportions. It's kind of like older stuff. And I'll kind of gloss over this. We'll use this in a problem, so I'll kind of mention these a little more detail in a second. But here's my confidence interval equations for the 3 different examples I had. So I could be looking at a proportion, a sample mean where I know the population variance, and then a sample mean where I only know the sample variance. And then down here I have my 3 test statistic equations. Okay? Same 3 different types of examples. It kind of reminds me that when I have a known population variance or I'm looking at a proportion, I use those standard normal or z-tables, or when I turn those into test statistics, they're z-statistics. And then if I'm looking at a sample mean where I only have a sample variance, I should be using the student t distribution, or when I calculate a test statistic, it comes from a student t distribution, so it's a t statistic. Okay? So that's just kind of talking through the formula sheet, kind of identifying these groups of equations. Now, I also have a reminder down here about a few things about hypothesis testing. It reminds me that the name or the type of the test is based off the alternative hypothesis. So no matter if I have a proportion or a mean example, if I have a greater than sign, it's a greater than or right-tailed test. Less than sign, less than or left-tailed test. Not equal to sign, and not equal to or a two-tailed test. And it also reminds me for a two-tailed test, when I find that area in the tail, I have to multiply it by 2 to get my p-value because I have two sides, right? Two tails now. So that's all on the formula sheet. What we're going to do is work through a few problems because hopefully these are kind of the easiest kind of points in the exam. So these first 4 problems, hopefully we can work through them relatively quickly. So I'll start on practice exam B here. There are YouTube videos of me working through all the problems on practice exam A and B. They're both split up. Each exam is split up into 2 videos. You can find that on our class's YouTube playlist. But here I'll work through it again. So let's say I've got the time spent waiting in line is uniformly distributed between 15 and 75 minutes. Okay. So let me switch this over to the dot cam here. Let me know if the audio has any issues as I'm switching to the dot cam to the regular. All right, there we go. So what I'm thinking about, anytime I see this uniformly distributed variable x, I should automatically just think about this visual, right? I've got a rectangle as my distribution where everything's equally as likely. It starts at 15, ends at 75. Kind of the general notation, here's my maximum D, here's my minimum C. Okay. We then said the height of this distribution, and we can be reminded in our formula sheet, the height of this distribution is 1 over that maximum minus the minimum. Okay. So here, I have my maximum, I have my minimum. 1 over D minus C is 1 over 75 minus 15, or 1 over 60. So it's just kind of thinking about what I'm working with here. So the first question asks, what's the mean? Right? Well, the mean of the uniform is just whatever splits it exactly in 2. So it's going to be the middle point between these 2 numbers. So all I'm really doing there to find the mean is taking my maximum plus my minimum dividing by 2, right? I'm finding the average between those 2 values. So 75 plus 15 over 2 should be what? 45? So that's my mean. Now, I'll show you where in the formula sheet I'm reminded of this, but I have this equation on the formula sheet. I also have an equation for calculating the variance. And the variance is simply going to be my maximum minus my minimum squared divided by 12. So if I want the variance here, it's just 75 minus 15 squared divided by 12. If I remember correctly, this is 300. Okay. So that's problems 1 and 2. Right? And the mean is pretty intuitive, especially if we have kind of the visual to go along with it. The variance, right, so here's my mean equation. Just add the maximum and the minimum and divide by 2. The variance is a little bit less intuitive, but it will always follow this formula when I'm looking at a uniform distribution. Uniformly distributed variable. So just for those of you, because I didn't switch over, I'm showing you where they're at in the formula sheet. Right, so here's the mean, here's the variance for my uniformly distributed variable. Right, it's always going to follow these 2 equations. Okay. Any questions on that before we keep moving? So that would be kind of my mean we found was 45, and that variance is 300. What if I wanted the standard deviation? What's the only other thing I need to do? I'm looking for the standard deviation here. If I have the variance, the standard deviation would just be, square root of the variance, right? So square root of 300. So what if I want to know what's the probability somebody waits in line more than 50 minutes? Okay. So that's what I'm trying to find in 3. So if I think about this, I know the mean is 45, and I want the probability that I see 50 or higher. So I'm looking for that area. Now, I know that if the mean splits this distribution in half, what should be the probability I see something above the mean? Yeah, 50% or a probability of 0.5. So I know what I'm looking for should be less than 0.5. Okay. And, 50 is pretty close to 45. At least it's a lot closer to 45 than it is 75. So this area is probably going to be close to 0.5, but it's a little bit less. Okay. So if I'm looking at the answers here, just based off of my drawing, first of all, I'm looking for a probability. A makes no sense. It has to be between 0 and 1. I know I said it can't be greater than 0.5, so I can rule out B as well. And then I'm going in between these two. Well, like I said, 50 is pretty close to that mean. So the area to the right is probably going to be pretty close to 0.5. If I'm going to guess, I'd probably guess D here. Right? But I don't have to guess. I can work through this. And I think the easiest way to do these is just think about, well, look, I already know the height of this rectangle, right? That's 1 over 60. The width is just going to be, well, I'm going from 75 to 50, so I'll take the difference between those two. So 25 over 60 or 0.42 here. This is a 4, not a 9. Okay. So I just look at the width of my rectangle. I'll always have the height if I just start out kind of drawing it out and thinking about that uniform distribution, that the height is 1 over the max minus the min. And that's just a matter of height times the width. Right? Any questions on that one? Now, if I had wanted to, I look at my formula sheet, it kind of tells me, well, you can find the probability of being in between any two values by simply using this equation. So I could have plugged in, if I'm looking at what I did here, really I could have plugged in my 75, plugged in my 50, that was the range I was interested in, and then divided by my maximum minus my minimum. Well, that's really what I was doing when I was multiplying by 1 over max minus the min. So I could plug everything in this equation and I would get the exact same thing. I just think that when you're using the visual and just thinking about the area of a rectangle, I've always found that's just a little bit easier. Right? That's all that is. Okay. So on this next one, I'm going to change a little bit. Okay. So here I've got the probability that somebody waits between 30 and 45 minutes. Okay. What if instead I use all the same values here, but I say I want the probability that I'm in between, so 75, 15, so I want what? The probability I'm in between 30 and 45, or between 50 and 65. Okay. So instead, I'm going to add a little bit onto that problem. What if I wanted the probability being between 30 and 45 or between 50 and 65? All right, so I can be in either one of these ranges. So I'm going to find the area of each one and then just add them together. I can do that because there's no overlap, right? There's no intersection here. So what I'm going to do, well, the height of my distribution is still 1 over 60. So here, it's going to be the length of my interval, so 45 minus 30, multiplied by the height. So I believe if we do this, we'll get 0.25. Okay. Well, if I know this area is 0.25, what do I know this area has to be as well? Yeah, it's the same length, right? 45 minus 30 is 15, 65 minus 50 is 15. Equally sized intervals, these are both going to have an area of 0.25. So when I add them together, the probability of being in either one of them would be 0.5. So I might ask you something like that in the exam. There's probably a reason why I'm changing this and showing you this, where I give you kind of two areas and you have to add them together. But usually there's something you can use where you know, well, if they're the same interval, it's really just adding those two up, right? They're going to be the same value, you just need to add them together. So save you a little bit of work there, right? You don't have to kind of go through and then plug 65 and 50 in if you notice that the intervals are the same length. Any questions over any of those uniform distribution problems? Okay. So we're next going to kind of go ahead and use this one. So we've got a random variable x. This is kind of going way back, where we've just got a variable x that's normally distributed. we know the population mean and we know somehow the population variance, right? So what we're going to be thinking about is we have this distribution for x. That variable x is normally distributed, and it's normally distributed around 460. And what? We have a standard, nope, we have a variance of 10,000 here, okay? Which makes it a little bit easier. What's the standard deviation? Well, it's just the square root of the variance. My standard deviation will be 100, right? So if I take the square root of 10,000, I get 100. So the very first problem asks, what's the probability that rent is greater than 600? Okay? So that's what I'm looking for. Automatically, what do I know that probability has to be? Less than, yeah, less than. The area to the right of the mean would be 0.5. I want an area smaller than that. So if I'm looking at the answers, I think I can rule a few. I can rule out A and B right away. So I know it's going to be either C or D. From there, I need to convert this normally distributed variable into a standard normally distributed variable. I found something above the mean, so my z-score should be positive. That's just something we should remember. Okay? And I'll show you where on the formula sheet in a second, but if I have a normally distributed variable, I turn that into a z-score by taking that variable x, subtracting the mean, and dividing by the standard deviation. Well, I have all this stuff. 600 is the x value I'm interested in, 460 is the mean, standard deviation is 100. I get, what, 1.4? Okay. So 1.4. Right. So from here, I'm just going to look up that value of 1.4 in my standard normal table. Right. So I go to my z tables. 1.40, so 1.40, 0.9192. Okay. Well, remember, the table always gives me the area to the left. I wanted the area to the right, so 1 minus 0.9192 or 0.0808. Okay. Any questions up to this point? Okay. Now, if I had for some reason done this math incorrectly in my head, so let's say I thought I could do this real quick in my head, not use a calculator, but I look at this wrong, and for some reason I think of this as being 1.6. And I look up 1.6, I would have found a different area to the left. When I subtract it from 1, I'd find, so I'd get the answer wrong, right? Well, this is on the short answer portion. If I see all this work, I can tell that all you did was make a simple computation error. I'll probably take like half a point off for that, right? Because you did the rest of the steps correctly. Even though these aren't the right numbers, it's because you made a mistake early on. So when it comes to that short answer, show me as much work as you possibly can. And that way, even if you get the wrong answer, like if you just write down, you know, maybe you had looked up 1.6 and you find, I don't know, 0.05 something, and you're just completely wrong. And I have no idea how you did it. You just wrote down 0.05. I really can't give a lot of partial credit. For all I know, you just decided to write down a number. And I don't know that you did any of the steps, right? So kind of write down as much as you can, as much of your work as possible. Okay.
Work will only get you extra points
on the short answer. Yep. So yeah, just on your upload for the short answer. Yep. Okay, but I would also say if you're doing all this work, almost in every single problem, you're going to be able to limit this in drawing it out. You're almost always going to be able to limit it down to like 2 options, right? Like in this one, we could rule 2 out pretty quickly, right? So, you know, it'll help you in the multiple choice portion as well. All right, so what if I want the probability it's less than 400 or greater than 520? Okay. So now I'm using the same setup. I've got this normally distributed variable x. Should be centered around that mean of 460. And I want to know what's the probability that it's less than 400 or greater than 520. Okay. Well, if I'm looking at this, right away, how far away is 400 from 460? 60 away. How far away is 520 from 460, the mean? Also 60 away. So these should have, once I convert these into z-scores. These should have the same z-score associated with them. It's just that 400 will be a negative z-score because it's below the mean, and 520 will have a positive z-score. So as a reminder, here my standard deviation was 100. So I'm going to use the exact same equation I did before. So take that cutoff value x, subtract the mean, divide by the standard deviation. So 400 minus 460 over 100 is negative 0.6. Well, because 520 was the same distance above the mean, I know it's going to be the same z-score, but positive. And I could go ahead and plug 520 in here, and I'd find that the test score, the z-score is positive 0.6. Because I know it's symmetric, I could actually do that pretty quickly without having to re-enter everything into that formula. Okay, so I'm looking kind of for these area in these two tails. So I'm going to look up negative 0.6 in my table. Z table. Negative 0.60, 0 is that first column, so negative 0.60, 0.2743. So the area to the left here, 0.2743, which means the area to the right of positive 0.16 would be the same thing. Now I simply just need to add these two together, right? If I add these two together or multiply by 2, so this is going to be kind of similar to like a two-tailed test almost in the way that we're doing this. But I get what? 0.5486. Am I doing the math? Yeah, it looks right. Okay. Any questions on anything there? I do this a lot in these types of problems. If I give you two values, usually that they're the same distance from the mean. So if you know those principles, it makes this one, you can work through it a little bit quicker. I might also do something like I say, okay, what's the probability it's less than 400? But greater than 460, in which case, do you even have to turn this into a z-score? If you're looking at the mean, what area is to the right? 0.5. So in that one, it would be a little bit easier. I only have to find this area and then add 0.5 to it. And I do something like that too. So you don't really have to calculate your z-score, and it's a little bit easier if you kind of remember some of these principles. All right. Any other questions on that one before we keep pushing forward here? All right, so 7 is going to be kind of important. I don't like to have cascading errors, and this doesn't necessarily mean you will, but it makes it more likely. So it's really important we understand a question like 7. It should be really easy points, okay? So let's say I'm dealing with that same variable. Notice this said use the information for the next 4 questions. Now I've got some new information for the following 2. I'm going to take a sample of 25 and calculate the sample mean. What will the distribution of that sample mean be? What will the mean of the sample means be, and what will the variance of the sample means be? Okay. Well, if I go to that formula sheet, first of all, just to kind of show you what I was getting that z-score equation, it's right here. I'm just dealing with a normally distributed variable. But now I'm looking at the distribution of sample means. And the variance of my sample means is simply taking the original variance and dividing by my sample size. So just as kind of a reminder here, I want the variance of my sample means. It's the original variance over my sample size. And we're not reminded of this in the formula sheet, but it's not really a formula. The mean of my sample means is always just the original population mean. Okay? So what I'm thinking about doing here is, well, the original mean of that data I sampled from was 460. So the mean of my sample means is 460. That should be really easy, right? The variance of my sample means is the original variance. Well, I don't have the variance here. I think it's all the way back here. So the variance was 10,000. So I'll take the original variance of 10,000 divided by my sample size of 25. And I get a variance of my sample means to be 400. Okay. So that's how it's as easy as that question should be. Right? It shouldn't be any more difficult than that. The only thing I could additionally ask you on the exam is, maybe I don't ask you for the variance, I ask you for the standard deviation, but that's simply just going to be one more step, which is to take the square root. Okay? Any questions on this one? This shouldn't be, I mean, this should be hopefully an easy question. Okay. So we use that 25 as our sample size. We get the mean and the, oh yeah, mean and the variance here. 460 and 400. What if I want to know the probability of being greater than 475 but less than 500? So this is probably one that's as difficult a problem as I would ever ask on the exam in terms of finding these areas, which are just, two values that are not the same distance from the mean, or, so it's going to be a little bit tricky. I've got to find two z-scores here. But what am I really doing, right? Well, I start out, I now know that I've got this distribution of my sample means, and it should be centered around whatever that true mean is. Right? I also, at this point, should have the standard deviation of my sample means, which was the square root of 400. Now, I'll kind of show you using the formula sheet why it doesn't matter necessarily if I got that incorrect, but it helps if I do get it correct. So I now want the probability that I'm in between, what, 475 and 500. That's what I'm kind of looking for here. So step one is I need to turn these values into z-scores. Okay. So I'm now looking for the z-score of a sample mean. It's going to be a little bit different. I'm now going to have a sample mean value that I subtract the mean from, but I should be dividing by the standard deviation of my sample means. Well, here, it was nice because I already had that calculated. However, I'll show you in the formula sheet, I also could just plug that equation in, which was the square root of the variance over my sample size. Now I could plug in the 10,000 here, the 25 here, or I could calculate it ahead of time and just plug in whatever that value is, right? Two ways of kind of getting to the same point. Now, if we look at the formula sheet, that formula will be reminded, where is it at? Right here, right? Here's how I find my z value for any sample mean when I know the population mean, right? I know the variable I'm sampling from. It looks almost identical to my test statistical equation. It's just that with my test statistic, I'm basing this off of a assumed true mean value. Okay? So at this point, it's just a matter of plugging these values in. 475 minus 460 divided by, well, I know this is the square root of 400. I could have, plugged in 10,000 and 25 here as well. And I get, what was this? I think this is 0.75. Let me double check this. So we got what? 15 divided by the square root of 400. Yeah, so I get a test statistic here of 0.75. Now, if instead I want to get the z-statistic for 500, the only thing that changes is I'm looking at 500 here. Okay? So now I've got what? 40 divided by the square root of 400. So that has a test statistic of 2. Any questions up to this point? Because I didn't specifically write out the z-score equation for that second value, but it'd be the exact same, just replacing 500 in there. Okay? So now what I'm going to do is I'm going to go to the table. I'm going to look up the area to the left of 0.75. I can also look up the area to the left of 2. If I subtract that smaller area from the larger area, I'm just left with what's in between, which is what I wanted. So final step, well, kind of final step. I go here, I look up 0.75, so 0.75. The area to the left of that is 0.7743. So that blue area, 0.7743. I then look up 2.00. The area to the left of that is 0.9772. Now it's just a matter of subtracting the smaller area from the larger area. So 0.9772 minus 0.7743 is what? 20, what, 29? No, I feel like that's wrong, but I'm sure the answer is here. So we'll see. I'm struggling to do the math in my head for some reason right now. 0.2038. I'm looking at this right now. So this is 0.2038 if we actually make that entered in. Okay.
Not that it really matters, but just to let you know, it's 7734, not 0.7743.
Sorry, say that again.
It's 0.7734 on the Z.
Oh, well, that would be why. Okay, thank you. Sorry, it was 0.7734. I was like, that doesn't match up. I know that this isn't right. So this should be 0.7734. That makes a lot more sense. Thank you. So once we get those entered in, and it kind of, even this shows that's very easy to kind of make mistakes there. But if I can see this work and I can see you right, like, yeah, I found this probability, I subtract this one. Even if you had that wrong, I'm probably taking on the, if this was the short answer, I'm taking half a point off for the computation. You're getting all the rest of the points because you really did work through this correctly, okay? Thank you for that, whoever assisted me there. All right, any questions on these before we keep moving? So I want to work through kind of a confidence interval and hypothesis test. Was that you or was that just a ghost? Okay. So we're going to switch over to practice exam A. because I want you to see, kind of work through an example with that student T distribution. Okay? So kind of line out before we jump into this. I said line out. I'm going to lay out, not line out. We've got three types of examples for confidence intervals and hypothesis testing. So sample mean, where we know the population variance, and sample proportion, in which case we always can use that standard normal or that Z table. The only time I need to use the student T is if I only have a sample variance and I'm looking at, I have a sample mean, I'm trying to build a confidence interval or do hypothesis testing for where the true population mean is. Okay? So proportion or known population variance, think standard normal. Okay? Only sample variance, student T. So what we were given here is I take a survey of 30 dentists. I find an average salary of $145,000, sample standard deviation. So I only have the sample standard deviation or sample variance. And I don't know the true population mean or variance. So build a 90% confidence interval for that true mean lies based off of our sample. Well, if we look at this formula sheet, here's our confidence interval equations. I've got a sample mean and only a sample variance. So I know it kind of reminds me, you got to be using the student T distribution. Okay? So I'm just going to rewrite this equation. We can kind of see, you don't have to rewrite it. You could just look at the formula sheet. But so that we have everything on the same page here, I'm going to write it down. And remember, really what this guy here represented, I could calculate this as an intermediate value. This is the standard deviation of my sample means. So, if I look at the information that I was given, I think I found a sample mean of 145,000. All right. My sample variance, well, I was given the sample standard deviation. So I had S, right? S was 10,000. So if I want the sample variance, I still need to square that. I then believe, was it 30 was my sample size? So now the only thing left I need to do is find that T value that gives me alpha over 2 in each tail. The problem specified we wanted the 90% confidence interval, so my alpha should be what? 90% confidence interval alpha would be, it's the area outside my interval in decimal form. So I'm going to divide alpha by 2 here. I get 0.05. And I think it doesn't even say in the actual formula sheet, instead of degrees of freedom, I think it actually tells you that degrees of freedom is n-1, right? It reminds you of that. So my degrees of freedom here would be n-1 or 30 minus 1, so 29. So I need to look up the T value at a degrees of freedom of 29. That gives me 0.05 in the tail. So I'm going to go to my student T tables here. I know the area I want in the tail is alpha over 2 or 0.05. Scroll down to my degrees of freedom of 29, 1.699. Okay. So that value here, 1.699. It's almost easier with the student T to do confidence intervals because I'm always going to be looking at the right side of the distribution. So I'm always going to be finding that positive value, which is what I wanted. Right? when I was doing confidence intervals using the standard normal, if I just look up alpha over 2, I'm always kind of looking at that left side of the distribution and getting the negative value and having to remember that's already built into my confidence interval equation. I add this margin of error to my upper bound, and I subtract to get my lower bound. Okay. Any questions on this? Okay, so, at this point, it's really just a matter of getting this entered into our calculator. Now, you'll notice, we switch to practice exam A here for this one, just a reminder. You'll notice that none of the lower bounds are the same. So once I find the upper bound or once I find the lower bound, I can correctly identify which of these is the right answer. So I really only have to find one of the two. I'll never give you cases where like you've got 2 answers with the same upper bound. So now I've got to go through, waste more time, calculate the lower bound as well to figure out which one it is. As soon as you find one of them, you should be able to correctly identify the answer here. So like if I do this one time, let's see. So square root of 10, 1, 2, 3 squared divided by 30 times 1.699, 145,000 minus that, 141,898. Yeah, so approximately, if you kind of round this to the second decimal, actually, sorry, round to the first decimal here, we'd have D. Okay. Any questions on this before we keep moving? Okay. All right. So that's our confidence interval. What if we want to do some hypothesis testing? So let's assume that some article says that the average dental salary is 150,000. You want to test for whether or not the true amount is less than that. So whatever we want to test for, and this is how I'm phrasing all of the problems like on the exam, is whatever I want to test for is my alternative hypothesis. So I want to see, is that true salary less than this reported amount of 150,000? So I assume the opposite is true, which is that it's greater than or equal to 150,000. So that's how I identify my null alternative. Whatever I want to test for, that's my alternative hypothesis. I then assume the opposite is true to find my null. So this one should be B here. Okay. Now, this one could be a little confusing because our sample mean was 145,000. We were given that information first. Whatever value you see as your sample mean, that should not be the value in your null alternative hypothesis. So we should be able to rule out A and C right away here. And then based off the way this is phrased, I want to know, is it less than 150,000? Well, sometimes it can be tricky to identify, okay, then is that a less than or greater than? Maybe I write it backwards on accident. But here, after I rule out A and C, because they're using the sample mean value, D can't be right, because what words or phrase should I kind of see in my problem if I have a two-tailed test? I should see different than, or is it different from, right? So I don't have that here. I have, is it less than 150,000? So I've got my null alternative hypothesis here. So I have a less than sign in the alternative hypothesis. So I have a what? Less than or left-tailed test. Okay. So I'm thinking about a left-tailed test, right? Automatically, I should know something is going to be true. And here we're looking at the student t-distribution because all we had is a sample standard deviation. If I look up a critical value, remember, this distribution, just like the standard normal, is still centered around 0. So for a left-tailed test, my critical value should be negative. Right-tailed test, critical values would be positive. Two-tailed tests, I'd have pairs of critical values. And we worked through some of those kind of Friday, two-tailed tests. So I want to find the critical value that maybe say gives me 0.1 in this lower left tail. So what I can do is I go back here. If I look, well, first of all, it's a left-tailed test. So this is where on the exam, I probably do something a little bit different here. After I ask you to identify the null alternative, I would then probably give you on the next problem, assume that this was, and it might use a different value, right? Instead of 150,000, maybe I say, assume that the true hypothesis was that it's, less than 158,000, right? I might change the value, but I'll make sure that we're all kind of starting off on the same foot. But because we're working on this one together and we can identify the correct answer, we have that. But I'll give you an assume true kind of test on the next one, right? But if I give you this as the assumed true test, we know this is right. Left-tailed test, I should have negative critical values. So I can rule out B and D right away. From there, it's a matter of going to my student t-tables. I know the alpha values I want to look up are 0.1, 0.05, and 0.01. So I'm going to be using these three columns. My degrees of freedom, still the same as when I was looking at a confidence interval, right? N minus 1, 30 minus 1 is 29. So 1.311, 1.699, 2.462. However, the student t-table always looks at the right side of the distribution. I'm looking at the left side. So it's going to be those same three values, but negative. So those same three values we looked up in the student t-table at our degrees of freedom of 29, but for a left-tailed test, they'll be negative. Okay. Any questions on that one? All right. What if I wanted to find the test statistic for the above hypothesis test? Well, let's go to my formula sheet. I've got my test statistic equations down here. I've got a sample mean, but I only have a sample variance. So this is going to be my test statistic equation. It's really just a matter of getting the values plugged in, right? I know my sample mean is 145,000. That assumed true mean that came from the null hypothesis, that was going to be 150,000. Sample variance, well, I had the standard deviation, so a similar thing. I'm going to have to plug that 10,000 in for S and make sure I still square it to get the variance, and then divide it by my sample size of 30. So really, calculating the test statistic is really just a matter of kind of getting our values that we've been given plugged in and getting the computation right in our calculator, or if you want to use Excel to be your calculator in Excel. Okay. However, if I look at this and think about what I can maybe rule out, the distribution of my sample means, I've assumed the mean is 150,000. I found a sample mean of 145. So when I turn this into a test statistic, it's going to be a certain number of standard deviations below the mean. So my test statistic here should be negative. So if I'm thinking about the answers that I can rule out, well, the only two values that could be possibly the answer are the negative values. So I can rule out C and D right away. Now, if I'm looking at, is it A or B? Negative 273. Hopefully, we've had enough experience thinking about test statistics and what they represent, the number of standard deviations away. This is an outrageous test statistic, right? Negative 273 would mean that the sample mean value of 145,000 that you found is 273 standard deviations away from that assumed true value of 150,000. It seems unlikely to me. If I'm guessing here, I probably guess A. And sure enough, if you go ahead and look at the answer key, when we plug everything in, oh, where is it? When we plug all those values in, we do get negative 2.74. Okay. Any questions on that step? All right, so let's instead assume that you find that the test statistic is negative 1.5. What levels can you reject at? So I said with these ones where we only have the sample variance and can only use the student t-distribution, that's going to be kind of difficult for us to find p-values. We can put it in a range, but we can't find a specific one. So we probably, safe bet here is to use the critical value approach. Well, remember, we already have the critical values here. Okay. So we had the critical values of negative 2.4 something, negative 1.699, and negative 1.311. Left-tailed tests, so our rejection regions are kind of to the left of those critical values. They correspond to 1, 5, and 10% significance levels. We then found we were then given an assumed true test statistic. So in case I, guessed negative 273 instead of the 2.73, where would that test statistic of negative 1.5 be? Somewhere over here. All right, that was my t-stat or my test statistic here. Well, it's in the rejection region at the 10% level, but not the 1 and the 5, right? And the reason why we know these were the 1, 5, and 10% levels, right, that was really just because alpha was 0.01, 0.05, and 0.1 here. So we can reject at the 10% level, but not at the 1 and the 5. So if we're thinking here, what levels can we reject at? Only the 10% level, given that test statistic was negative 1.5. Okay. So we can make our critical value rejection decision still pretty easily with these student t distribution examples. Okay. So 20 is probably one that's going to be a little bit harder than anything that we have here. So let's assume, what we had instead was, instead of a sample size of 30, I had a sample size of 60. So what's that going to alter, right? So my sample size has went up. Okay? Well, if we think about what our test statistic equation was, we had the sample mean minus the assumed true mean divided by the standard deviation of our sample means, which was the sample variance over my sample size. Okay? So what's going to happen is if my sample size goes up, and you could recalculate all this and prove it to yourself. So if the sample size goes up, the standard deviation of my sample means goes down, right? Because that denominator is larger. So now if my standard deviation of my sample mean goes down, what happens to my test statistic? Well, a smaller denominator actually pushes up my test statistic. If I see a larger, and when I say up, larger in absolute value, right? If it's negative, it becomes a larger negative value. So if it pushes my test statistic to be a larger negative value, well, remember the p-value would be the probability of seeing something as far away as you did or even further. So notice if I had tried to calculate my p-value, it becomes smaller, right? So this larger test statistic will lead to there being a smaller p-value. And if we only reject when the p-value is less than alpha, if the p-value is going lower and it's getting smaller, then it's more likely that we can now reject, even if we see the same sample mean value, but we saw it from a larger sample size. Okay? So that would be a good one to know. Probably think that's kind of tough. I kind of do too. So there might be, that would probably be a bonus thing to know, So that bonus question there, maybe you can kind of guess what that's going to be related to. But that's how you would kind of walk through a problem like that, okay? Or kind of think about how to make that statement, right? So we didn't have a smaller test statistic. P-value wasn't larger. We were more likely, right? And here we were just looking for the one that was true. So C was the only one that was true. Any other questions for me before we end here today? So, if it was me, I'd work through these practice exams, look at these answer keys. They kind of have some of the formulas and a little bit more help here. If you have questions on any of them, feel free to reach out to me, or kind of consult one of those videos that I posted of me working through the different problems on the practice exams. If there's no questions, I'll be, keep an eye on my email if you have any last minute kind of study questions for me. And good luck as you take the exam. We'll meet again on Wednesday.